Oh.
Is that how you're gonna start your
Recording.
Okay, so we're talking about stoichiometry. Stoichiometry is the mathematical manipulation of chemical data using the mole. It's as much fun to do as it is to say. Stoic. I just like this word.
Stoic?
It's kind of like stoic, but you won't be stoic about stoichiometry because it's so much fun. Stoic means lack of emotion,
Yeah, that's about
but you won't have a lack of emotion about this. This is so much fun. Okay, so consider the balanced equation. 6 carbon dioxide molecules plus 6 water molecules gives you 1 molecule of sugar and 6 molecules of oxygen. How many moles of carbon dioxide does a plant need to absorb to make 1 mole of sugar? The answer is 6. And so one of the things you can do with moles is to create mole ratios of equations. And you can look at this and say, well, according to the balanced equation, 1 mole of sugar, because the assumed coefficient there is 1. 1 mole of sugar is made by 6 moles of water and 6 moles of carbon dioxide. It's a 1-to-1 ratio of carbon dioxide to water, but it's a 6-to-1 ratio of carbon dioxide or water to sugar. And so you can use the coefficients here as mole ratios and say a certain relationship of moles of this thing make moles of this thing. And we did a little bit of that with the lab last week, 2 weeks ago, 3 weeks ago, last time we were with each other. And so you've seen that concept a little bit more. And we're going to expound on that idea and go more into detail with that today. So we're going to create something called a coefficient bridge. A coefficient bridge. The coefficients in the reaction are things that will help you see what the relationship is between products and reactants, or products and products, or reactants and reactants. And then you can use that mathematical relationship to determine how many grams of something you need, or what volume of something that you need, based on the characteristics of that substance, the molar mass, and the relationship of how many moles to how many moles. Okay, so a coefficient bridge is the first concept. And I don't know if I gave enough time to write that down, so I'm going to pause here for just a second. So having a coefficient bridge allows you to predict the number of moles of a reactant that you need to complete a reaction to get a certain amount of product, or the number of moles of product that you're going to expect out of a reaction. So if you were an industrial chemist and you're making something, you're making a chemical, you need to know how much of the ingredients to mix together to make a certain amount of product. The lab that we did week 14, last time we were together, showed that the most efficient production of the product is when you mix together reactants according to a particular ratio that is determined by the chemical equation. And otherwise you're wasting reactant, right? So if you've got substance A and substance B that you mix together to make substance C is what you're going to go sell, right? You're making this product for the world. If you have too much of A and not enough B, then you're wasting A, because B is going to react, but you've got a bunch of A left over that you can spend money on. And the product that comes out will not be as much as it could have if you'd had the right balance. So this is very important for industrial chemistry, for applications where you need to make a certain amount of something. This helps control costs and all of those business aspects of chemistry. It's also important in medicine. If you're taking a certain amount of medication, that's going to react with some substance in your body to produce something, to change and do something. If you take not enough medication, then it's not going to react with all of the whatever in your body needs to react with, and you're not going to have the result that you need. If you take too much medication, then it's going to react with everything that's present in your body, but then there's going to be drug left over, and who knows what else that's going to do, and you can have bad side effects. So it comes into play as well in dosing for medications. It comes into all kinds of, comes into play lots of different areas in chemistry. So we need to be able to predict how much of these things we're going to mix together and how much of this thing we're going to get at the end. And then obviously there's no such thing as like a mole scale. You can't pour something in, the scale reads 3 moles because it doesn't know. So in order to be able to weigh out a certain amount of something, you've got to use the mole mass relationships from the first part of this chapter, from 9a, to determine how much weight, how much mass of something you need to have a certain number of moles of that thing. So some examples here. If a plant had 3 moles of water available to it, how many moles of sugar could it make? So it has 3 moles of water available to it. We're going to assume that carbon dioxide is in excess. How many moles of sugar could it make? Well, the relationship is 6 moles of water to 1 mole of sugar, so shouldn't be too hard for you. If it only has 3 moles of water available to it, it's going to make half a mole of sugar, right? So the molar relationship is 6 to 1, 3 moles of water, 3 times the relationship of 1 to 6. Moles of water cancels out, multiply across, you get half, right? And without doing all of that complicated math, you can see if it's got half of this, then it's going to have half of that. So that is an example of the kind of thing that we're going to be doing, right? If a plant produced 18 moles of oxygen as a byproduct, how much sugar was made? It produced 18 moles of oxygen as a byproduct. How many moles of sugar? 3. Okay, you guys see how that worked? 6 moles to 1 mole is the relationship. So if it made 18, then 6 to 1 relationship would mean that this is 3. And I'll show you the math. The molar relationship is 6 to 1. 18 moles of oxygen, the relationship is 6 to 1. Cancel out the terms there. 18 moles of oxygen divided by 6 is 3 moles of sugar. Okay, so that produced 3 moles of sugar. You guys understand how you use these things? No. Where did I lose you? The beginning. Start at the very beginning. So the numbers as the coefficients here are ratios. 6 amounts of this to 6 amounts of this to 1 amount of this to 6 amounts of this. It's a relationship of ratios. So using the ratio, if I'm given a quantity of one of these things, I can use the ratio to determine the quantity of the other. So if the relationship is 6 to 1, because there's 6 moles of oxygen to 1 mole of sugar, the relationship is 6 to 1, 6 moles of oxygen to 1 mole of sugar. And I have made 18 moles of oxygen as a byproduct, 18 moles of oxygen, then I can use my bridge notation to convert moles of oxygen to moles of sugar. 18 times 1 is 18. 1 is underneath here, the assumed number underneath. 1 times 6 is 6. Divide, and I made 3 moles of sugar. So it's just using ratios from the coefficients to determine a certain amount of something. If I know something else that I got, yes. So the water one was 6 moles of water to 1 mole of sugar. So if the plant only has 3 moles of water available, it's got half of that number. It's going to make half of this number. Right? It's just it's a ratio relationship. So the same thing, 6 moles of water to 1 mole of sugar, 6 moles of water to 1 mole of sugar. And so 3 moles of water, I just have to convert moles of water to moles of sugar. The units cancel out. 3 divided by 6 is half. So it's just like converting fractions. Okay? All right. One more time. If a plant had 24 grams of water, now it's getting a little bit more complicated. If a plant had 24 grams of water stored for the purpose of photosynthesis, how much sugar could it make? So we already answered the question of mole ratio if I know how many moles of water. But now I'm telling you how many grams of water. So I have to convert first grams to moles. First we need to determine the number of moles of water, right? So water's molar mass is 16. And if you don't know how to get that, the molar mass of something is all of the atomic mass unit numbers in your periodic table. So hydrogen up in the top is 1.008, and oxygen is 16. If you add them together, I'm rounding there for the hydrogen. If I'm if you add them up, you get 18 grams per mole, right? 16 grams for oxygen, 1 gram for hydrogen. There's 2 of those, H2O. So you get 18 grams-ish as the molar mass of water. 24 grams of water divided by 18 grams per mole gives me 1.33 moles of water. So that's how many moles of water I have. So first I needed to get the molar mass and figure out how many moles of that substance I have. Now once I know that I have 1.33 moles of water, I can use the coefficient bridge, 6 to 1. 6 moles of water to 1 mole of sugar. So 1.33 moles of water, and the relationship is 6 moles of water to 1 mole of sugar. So I need to cancel my like units. Converting moles of water to moles of sugar, 1.33 times 1, 1 times 6, so 1.333 divided by 6, 0.222 moles of sugar. Okay, so I was asked how much sugar. Oh, I didn't specify in the question if I was looking for grams or moles. So it can make, oh, space error, 0.222 moles of sugar from 24 grams of water. If I wanted to, I could also ask you how many grams of sugar will I make from 24 grams of water. And then you would have to find the molar mass of sugar and go back through the molar mass of sugar and 0.222 moles to get the grams. Yes? Atoms. Yep. Okay, so stoichiometry uses the coefficient bridge and molar masses to calculate the amount of products or reactants that you need to make a reaction happen. Okay, go ahead and take a moment and write that down. So just like in that last example, if you have an amount of reactants and you use the coefficient bridge to calculate how much product you're supposed to get, that's called the theoretical yield. So the 0.222 moles of sugar that we should have gotten from that reaction would be the theoretical yield. I could then do that reaction, let the plant use its 24 grams of water to make photosynthesis, somehow get all of the sugar out of that plant. This is a hard thing to do, but weigh the amount of sugar that plant made, and then I could calculate the actual yield, right? How much did I really get versus how much I thought I was going to get, and that creates something called the percent yield. So this is a ratio of how efficient was my chemical reaction. I was supposed to get a certain amount of something, and in fact I got this amount of something. And you can express that as an efficiency or as an accuracy and report the percent yield. You will do this a lot in college chemistry classes, organic chemistry especially, if you wind up taking that class, where they will say, hey, go through this long process and make this compound. And then after you're done making it, weigh how much you got. And then they want to see how good were you at all of the steps in making this compound. If you only got 4 grams of it, but you do the math and you should have made 20 grams of it, well then you screwed up somewhere because you didn't do some chemical reaction right and a lot of your stuff went away and didn't turn into what you thought it was going to turn into. And so you'll express a percentage yield and say, oh, I only got 4, I was supposed to get 20. I only made 20% of what I was supposed to. And so that is it's a way of grading yourself as a chemist. How good are you at doing what you're supposed to do? And again, going back to any kind of industrial chemistry where you're making a product, you're making a drug, you're making paint, you're making any substance, you're making plastic. You buy enough ingredients to produce a certain amount of product, and you plan on selling the product so you can buy more ingredients and have a business. But you do your budgeting to make, I don't know, a ton of product from a certain set of ingredients, and instead you only wind up with 20 pounds of the stuff. Now you're in trouble because you can't sell that for enough money to buy more of the other thing you need to be growing. You're out of business. So percent yield comes into play with a lot of applied chemistry. Here in our class, you will do a little bit of playing with percent yield, just so you've done it once, but we're not making a product here, and you're not selling anything. And so this is just going to be an academic exercise. But if anybody ever winds up in any kind of manufacturing realm where you're making something, this definitely is applicable to many industries. So theoretical yield, what does the math say I should get out of this? Percent yield, what did I actually get? How good is my process? How efficient is my process? Am I losing out on things that I should be making? Okay, so here's an example again, going back to our balanced photosynthesis reaction. In the previous example, if the plant actually made 0.213 grams of sugar, what was its percent yield? And this is a typo, because it's grams and the last one was moles. We'll forget about that. Sorry about the typo. Let's say it was supposed to make 0.222 grams of sugar instead. And instead we made 0.213 grams of sugar. So percent yield is actual divided by theoretical times 100%. So it actually made 0.213 grams. It was supposed to make 0.222 grams. So 0.213 divided by 0.222 times 100%. I get 0.95945 times 100% is going to be 95.945%, and I would need to correct for significant digits and say that I was 95.9% accurate, or 95.9% efficient, right? I had, that's a very good result. You only lost 4% of the possible product that you made, okay? So percent yield is just a simple, how much was possible, how much did you get, just like calculating the grade. Okay? You guys understand the concept? Yeah. Alrighty. Yippee. Good, take a moment, write that down. I love making banana bread. Do you like making banana bread? I love banana bread. It's fabulous. Especially when you have those black bananas sitting around that nobody's eaten in your family, and they're looking at you like either throw me away or turn me to bread, right? So we had that problem at home over the break. Bought bananas, didn't eat them fast enough, black bananas. Yeah, don't eat black bananas. I'm gonna make banana bread. So I open the pantry, and I've got enough bananas to make 2 loaves of bread. And I open the pantry, and I only have 1 cup of flour. I can't make banana bread. Those bananas are going both ways. So instead we made some banana muffins, because we only had 1 cup of flour. I wound up having to throw away a bunch of bananas. It's very simple. That's a problem with a limiting reactant, right? You have 2 things that you're supposed to react together to make product. And you've got truckloads of one thing, but not enough of the other thing. And so they'll react and they'll make your product, but they're only going to react until the one that you're going to run out of first runs out. And then you can't keep making the product when you've run out of one of the reactants. I can't make 2 loaves of banana bread with 1 cup of flour. And so I was only able to make a couple of muffins because that's all I had. And so I could have gone to the store and bought more flour, but instead I threw away the extra bananas. I know, it's wasteful, it's horrible. But that's what I did. So the flour was a limiting reactant. I ran out of flour, and I still had bananas left over. Bananas are the excess reactant, okay? So if you have a balanced chemical reaction, you know the coefficient bridge, you know how the amount of this thing is supposed to relate to the amount of this thing. If you don't have them in perfect balance, you're going to have a chemical reaction until one of them runs out. And you can predict which one's going to run out first, and you can predict how much of the other stuff you're going to have left over. Okay, you can do all of that math with the balanced chemical reaction. So back to our photosynthesis reaction here. If the plant were in a greenhouse, so it's enclosed, it's airtight, with 184 grams of carbon dioxide, you went out and weighed all the carbon dioxide in the greenhouse because you have no life, okay? And so 184 grams of carbon dioxide, and it had 19 grams of water in its tissues and in the soil. which reactant is limiting and which reactant is in excess. So first, I need to know how many moles is 184 grams of carbon dioxide and how many moles is 19 grams of water. Because the relationship between carbon dioxide and water is 6 to 6, or you can reduce that to 1 to 1, right? It's supposed to have as many moles of carbon dioxide as it does of water. So I need to use my molar mass, and I need to find out how many moles of these things I have, okay? So the molar mass of CO2, 12.01 plus 2 oxygens at 16.00 is 44.01 grams per mole. So if I have 184 grams and every mole weighs 44.01, then 184 divided by 44.01, I have 4.1809 moles of CO2. And that's not correct for significant digits, but I'll leave it there for now. Because remember, you only round at the end. So 4.1809 moles of CO2. Now, the molar mass of water is 16 for the oxygen and 2 times 1.01, that's the hydrogens. So 18.02 grams per mole is the molar mass of water. So I have 19 grams of that. 19 divided by 18.02, I have 1.0544 moles of water. So looking at this, I have 4 moles of CO2 and 1 mole of water. I'm supposed to have as many moles of CO2 as I do of water. So what is limiting? What do I not have enough of? What do I have not have enough of? Water or CO2? Huh? Water, right, yeah. I have 4 moles of CO2 and I have only 1 mole of water. And I'm supposed to have an equal amount, 6 to 6. It's a even ratio, right? So I don't have 4 and 4, I have 4 and 1. So water is my limiting reactant. Okay? The molar mass is 6 to 6, which is the same as 1 to 1. For every mole of CO2, there should be 1 mole of water. There is not. There are many more moles of CO2 available than water. And so water is my limiting reactant. I'm going to run out of water before I'm going to run out of CO2. And CO2 is in excess. Okay? You guys understand the idea? Yeah. Water is like my flour, and bananas are like CO2.
So they just have to be equal?
They would need to be, yeah, in whatever ratio it is in the equation for them to be balanced. And in the real world, not usually balanced. So you look at what you have, you look at what you should have, and you say, okay, I'm going to run out of this one before I run out of this one. Okay? That is actually the end of the slides. Are there any questions? Any questions? Any questions? Okay. You will get to practice.